Hola, bueno, profesionales de varios países. Entre esos nos encontramos nosotros, en el que hace varios años ya venimos colaborando con distintos profesionales, investigadores y estudiantes de esta universidad, y tanto relacionado a trabajos de teología estructural, pero sobre todo aplicado a la explotación geotérmica, tanto en el subandino como en la puna, ¿sí? También aprovechamos para avisarle que, gracias a la profesora Invernizzi, ella es actualmente la encargada directora de el curso sería de bachiller, los 3 primeros años de la carrera de geología en la Universidad de Camerino, y nos encontramos en la confección de un convenio de intercambio, primero de entendimiento y después de intercambio, entre la Universidad de Camerino y la Universidad de Salta. Así que para mí es altamente gratificante, que seguramente en el próximo mes lo vamos a poder lograr, y esto sería para que tanto estudiantes y docentes e investigadores de nuestras carreras puedan realizar estadías e intercambio, visitar los laboratorios y, por qué no, avanzar hacia actividades de proyectos y demás que permitan desarrollar las actividades tanto formativas como de investigación de nuestros profesionales, nuestros alumnos y toda la comunidad universitaria, porque también involucra a los docentes. Así que muchas gracias por venir. También le damos la bienvenida a la gente que está por YouTube. Cualquier consulta o preguntas que surjan durante la charla, la pueden dejar por ahí en el chat de YouTube, y trataremos de dar respuesta a eso al final de la charla. Si bien la charla la pusimos 9 a 1, fue un error mío, yo pido disculpas porque en realidad es el horario que está reservado al auditorio, pero la charla va a ser, calculamos que de 2 horas por ahí, ¿sí? Así que seguramente vamos a hacer un break al medio para que no se haga tan largo, y nada, muchas gracias por venir, y nuevamente gracias.
Muchas gracias.
Ah, sí, sí.
Muchas gracias. Unfortunately, I don't speak Spanish, so my presentation will be in English or sometimes a mix of Italian and few Spanish words that I try to pronounce it. So, ho mucho gusto de estar aquí. Mi experiencia de trabajo con profesores, researchadores de esta universidad más lunga, 13 años, dal 2011, e abbiamo compartito ricerche nell'area subandina e alla Puna. Now, today I'm here to talk about food inclusion. That was really a great love for me. And I was involved in studying food inclusion for several years, starting from my postdoc and later on during my time as a researcher at the University of Camerino. And as Ruben Philly said, I was working with several different researchers in different laboratories, but my school, my experience of food inclusion started with the Virginia Polytechnic in Virginia, in the US. And so my first research together with, with those researchers. Now, I divided my presentation in two parts. The first one is more theoretical, so I will show you what are food inclusion, how they work, and some characteristics about food inclusions. And in the second part, I will show you few case histories, so few applications from my research and from a research of a colleague of mine. Now, food inclusion are known by several years. Firstly, in the 16th century, some researchers get the feeling that there was something inside crystals, something moving, some bubbles, something like that. But of course, they didn't know what it was. And later on, there were experiments by these researchers rather that tried to make silicate liquid immiscibility in magmas. So with some experiment adding iron to some oil and water, it started to make experiment on fluid inclusion. But we have several pieces of historical paper. This is by Boyle, for example, in 1672, and he describes as firstly he saw something inside the crystal, something inside the stones, and so he wrote about this. And then during the 19th century, several researchers made observation, and particularly Heraclitus Sorby, he was really describing and making the first thinking on the behavior of fluid inclusion. So you see some of the drawn by these researchers that already got the feeling about the presence of fluid with a bubble or crystals inside fluid and inside inclusion. So he described several characteristics. And so these are some pieces of work by Sorby in 1857. So on the microscopical structure of crystal indicated the origin of the area. So we got the feeling that these little drops of liquid or of fluid inside the crystal can testify something about the origin of the minerals and the rock, which is the core business with fluid inclusion. So what are fluid inclusion in fact? So there are small volume of fluid that can be liquid, vapor, or also solid occluded inside this trap within the crystals, and then they generally originate, they start with imperfection during the growing of the crystal. And or you can have other kind of fluid inclusion that we call secondary. We will see that are produced during subsequent healing of fractures when fluid circulates inside the rock. So you have two kinds, mainly two kinds of inclusion, some coming from irregularities during the growth of the crystal, and these are called primary, and some that represent solid fluid entrapped around field fractures. So we can describe them as time capsules. So there are really little pockets where pressure, temperature, and composition of the initial fluid are preserved. And in the case of diagenetic system, they really are the direct, how can I say, the direct testimony of the diagenetic system. You'll see something very nice. This is a beautiful foot crystal with a very large inclusion that is a liquid with a bubble inside. But these are things for museums, you know. you are not generally so lucky in studying inclusion. So generally, fluid inclusion consists of a use to concentrate water solution with various salt dissolved or elements or elements and atoms dissolved in it. And so you can have sodium, chlorine, or potassium, calcium, magnesium, and so on. Most commonly, the fluids trapped within the inclusion are aqueous solution, variable salinity, but you can also have volatile phases like CO2, CH4, or nitrogen in different proportion. It depends what is the origin of the inclusion, of course. You can have hydrocarbons or aqueous solution with variable salinity containing also hydrocarbons, so some immiscible fluids trapped within the inclusion. Why we are interested in fluid inclusion? What can we do with this stuff? So currently they are really applied in several different fields. For example, when I started to apply fluid inclusion in structural geology problem, because I am a structural geologist, nobody was doing it. So we tried, me and a researcher from Pisa, which is called Chiara. She was working and still works in the Himalayas, so maybe in magmatic and metamorphic rocks. Sorry. Okay. And we were the first, almost the first, to try to apply the study of fluid inclusion in structural geology questions, try to answer to some of these questions. But generally, they were already used in ore deposits to study the genesis of ore depositing and mining exploration, for geothermal environments, to reconstruct the evolution of geothermal systems in oil exploration, to the can be applied sedimentary and metamorphic petrology, of course, as I said, structural geology and gemology. So you can have very many fields where you can study. So what can you do with this? Study fluid inclusion. You can get information on fluid rock interaction processes, for example, in geothermal fields, or the genesis of the mineralization in hydrothermal oil deposits, thermobaric reconstruction of metamorphic and contact metamorphic complexes, and we will see examples about these, and the study of the relationship between tectonic structure and fluid flow. An example I will show you in the second part. And also, they can be useful nowadays for natural analog of CO2 mineral sequestration, so recent applications. Where we can find fluid inclusion, in which mineral is it possible to study fluid inclusion? Oh, plenty of minerals. Of course, the most used are quartz and calcite, but you can use also fluoride. Frequently, you can find in fluoride, halite, apatite, and others. We see some of them. And the colleague of mine, also in garnets, she was working a little bit in garnets. So many minerals, all minerals can contain. Of course, it is possible to study inclusion when you get transparency of the mineral, because you have to watch and to see, in particular, the phase changes inside the mineral. So if the mineral is not transparent, you cannot study anything about fluid inclusion. When you start a study of fluid inclusion, the first thing is you have to have a question to answer to. And this will drive everything. Will drive how you will sample, what you get as sample, and will drive also the several steps of the study. And in particular, the first step is the phylogenetic study, when you study the inclusion, to see when they were trapped with respect to the mineral growth. And you will check all the visible features, so the different phases which characterize the inclusion, which are recognizable at room temperature. So what you get at the beginning is a temporal classification of the inclusion inside your sample, trying to constrain the timing of tracking and relative to the mineralization and the structural event that affect the inclusion. And of course, at the beginning, you make observation at room temperature, so looking under the microscope, and you will see the different phase present in your inclusion, and you can get first information about the composition of the inclusion, and so on. So you get the feeling on what you can do with your sample. What means paragenetic classification? It means to try to recognize if your inclusion were formed during the mineral growth, the crystal growth, or in a second phase, in, let's say, the deformation of your crystal. So the so-called primary inclusion are those which are related to the mineral growth, and you can have different features to get confident that your inclusion are related to the mineral growth. But as well, it can be very interesting to study the secondary inclusion. So the first are called primary inclusion. What about the secondary inclusion? They are trapped after the mineral growth, and generally they are aligned along fractures, which now are not more fractured. They are healed and they trap some little drops of fluid. So they are due to some kind of brittle deformation and recrystallization subsequent to the crystal growth. But you can also have pseudo-secondary inclusion because the life is always complicated. So inclusion, they are trapped during a kind of deformation while the crystal was growing. So, for example, look at this image here. These are pseudo-secondary because you recognize different phases of the crystal growth with these boundaries, and we have inclusion aligned along the boundaries, which will be primary inclusion growth during the crystal growth. This structure is pseudo-secondary because it was an accident during the mineral growth, but then it stops here and does not continue. While if you have fractures cutting through the growth surfaces, these are secondary inclusion because they are along fracture developed in a secondary phase. Okay. So of course you can have several defects that allow the growth, the fragment of inclusion during the mineral growth. We see here an imaging where you get inclusion, these dark stuff. Some of them are that are visible, other are probably in this case they are decrepitated, which means they are not preserved. They were there, but they are not still there anymore. But they were for sure primary because they are aligned along, you see, band of growth of the mineral. And this is another image to explain how this is from the Bible of fluid inclusion, which is a fluid inclusion book by Reder, which was really the father of the modern study of fluid inclusion. Edwin Reder. I think it's possible. Sorry. So you see some defects, some holes in the crystal that trap the fluid. Or as we have seen before, these are aligned along growth surfaces because the growth surface is irregular, or some fracture during the growth, so pseudo-secondary inclusion and several cavities that can attract the inclusion during the growth of the crystals. And I'll show you another picture. This is from another book, Goldstein and Reynolds. They worked a lot in sedimentary environments, so they describe everything about the development and the significance of fluid inclusion in sedimentary environment. And you see here, for example, inclusion distributed primary inclusion distributed inside calcite crystals. And this is a picture by me many years ago. It is out of focus, but I wanted to do it just to show you again the surfaces through the deep focus of the crystal. Because as I probably will say later on, I'm not sure, the sample that you have to prepare to study fluid inclusion is not a normal thin section. It is a thick section. Generally, it has a thickness between 150 to 200 microns, because you need to look through the mineral. So you have to preserve the transparency, but you need to look through to have the feeling, for example, if you have a field fracture, so your inclusion are aligned along the plane, or you have primary inclusion and what is the position. And in this case, you are looking through the crystal and you see the groove surfaces, several groove surfaces, and so you are sure these are primary inclusions. This is again from a book with the distribution along groove surfaces, and this is the schematic drawn of this kind of inclusion. Perhaps you've got the feeling that these are tiny features, so very small usually. Generally, you work with microns. Fluid inclusion starts to be visible and measurable around 3-4 microns of dimension. It depends on the quality of the crystal sample and on the quality of the microscope, of course. And more often you work with inclusion between 5 and 15 microns. If you are lucky, you get in inclusion 20, 25, 50 microns is a giant, you know, and it's very easy to study. This is a natural example. These are all examples of primary. Oh, sorry, no, these are primary again. These are very nice, very well developed, quite bright and easy to see. Also here, they are darker, but you can recognize in several of them the little bubble inside. And so when you get the bubble, you get the feeling that it's possible to do some measurement. Otherwise, it is really different. And these are pseudo-secondary. So you get some stop of the fracture somewhere. And definitely secondary inclusion aligned along plane. And when you focus with the microscope, you see the plane and the attitude, the orientation of the plane inside the crystal. So you get, you're sure these are secondary inclusions. And this is a diagram I showed you also before, again from radar, just to understand what happens when you are healing a fracture. So you get a fracture and fluid goes into the fracture. And then gradually you heal the fracture. You heal, I don't know another. Okay. But you left behind little pockets of fluids. So some parts crystallized and some little pockets, and these are the distribution of your secondary inclusion. And this is again a fracture, a healed fracture of secondary inclusion from one of my study. And this was one of the amazing ones. You see, you get a lot of inclusion, and all of them are quite nice with the bubble, very similar. You get the feeling that they are all the same event, because the bubble is equal dimension in all of them. And so when you will go to measure, they will give you good results. If you have different percentage of bubble, for example, you don't get good results. And we will talk about this later on. And other pictures just to see the traces of secondary inclusion again in a calcite crystal. I put this image in here just to tell you that many times when you study fluid inclusion, you are interested in making a story. So try to understand several steps, perhaps to see the evolution of the environment, to see the evolution of the fluids inside the crystals, if there was changing, and cathodoluminescence, that is one of the facilities you have in your lab. is a good way to check different phases, different stages. For example, you can get different bands of growing of the crystal. So you will try to measure inclusion in different bands to see if there was any evolution. Or you can get, feeling of fractures with some differences from the host grain. And again, you can distinguish several, we call them spheres, fluid inclusion assemblages. So catecholuminescence is a very good facility to get the evolution of the inclusion. And so in this picture, colored picture, we have several examples, Hydrothermal cement, Pleistocene brachiopods. So you can get the difference in the fossils with respect to the matrix and to the cement and so on. Other example, just to get a list of examples and to see also that it's not so easy because you know sometimes inclusion are very dark, sometimes they are really tiny, sometimes it's not possible to see anything, you cannot measure anything at all. Another example again, I think that some of them are, because it's 2014, some of them should be inclusion from the La Candelaria Ridge, because we made some analysis when we did the first work in Rosario della Frontiera, in a geothermal system at Rosario della Frontiera. And our goal that time, one of our goals was to see the effectiveness of the cap rock. And we use inclusion, grid inclusion, together with the vigenite reflectance and elite and smectite layer minerals, clay minerals, to get the paleo temperatures. And so I studied the grid inclusion in some veins related to the thermos area where the geothermal fluid was rising up. And then we compare these results that gave temperature, tracking temperature for the inclusion around 110, 120 degrees. We compare with an area without any fluid rising, okay? And in fact, we got much less temperature, around 60, 70 degrees. So it was a proof that the cap rock, where the geothermal system was preserved, the cap rock was good. So no heat was lost through the cap rock. Now, please stop me if there is something that you don't understand or is not clear or whatever, or any question. So, I mainly talked about the bubble inside the inclusion. So what can we recognize at room temperature in the inclusion? So what we can get are one phase. So we see just one phase inside. We get two phase, liquid and vapor. In this case, this is a liquid-rich inclusion. So you see more liquid than vapor bubble, or vapor-rich inclusion. More vapor than liquid. You see the meniscus here. So the liquid is just in two pockets at the ends, at the edges of this inclusion. In this case, you have light-bearing inclusion, which means there is a lot of salt dissolved. So you are above the eutectic composition.
Hay un límite para medir, por ejemplo, lo que se mide para la extracción fluida, las burbujas o el líquido tienen que tener un volumen mínimo o un tamaño mínimo para que uno lo pueda medir. Porque, por ejemplo, en ese menisco de ahí, ahora vamos a medir. ¿Hay espacio para medir las dos fases, por ejemplo?
Spazio per misurare.
La vapor phase o el líquido.
So you want to know what you can see?
Or what can you need? If you are liquid vapor, for example, you need
There is a threshold
Well,
volume or
no, there is not a,
area
yeah, there is no threshold. Of course, you will have the homogenization because what we are going to do with the fluid inclusion, mainly, the first step is the microthermometry. What is microthermometry? We will talk about this. Microthermometry is a technique to produce phase changes inside the inclusion. So this is what you see at room temperature. Then you increase the temperature to homogenize the inclusion. So in this case, your homogenization will be to liquid. So you will see the vapor bubble disappearing. In this case, your homogenization will be to vapor. So it's the liquid that disappears. And of course, you have the come si chiama, diagram of stability, and you will put your inclusion in the precise place in the diagram. In both cases, if you have the liquid homogenization of the bubble homogenization, but you don't have a limit. It doesn't matter if you have just a film of liquid or more liquid. Okay, you can develop crystals if the salinity is higher, so it's above the solubility, and you get the crystallization. In this case, highlight crystallization. Or you can have also miscible fluids. Like in this case, you have liquid water, and then you have two phases of vapor relative to CO2. So you have a vapor CO2 and liquid CO2. And so you get two meniscus inside. It is amazing. And you will get the homogenization, generally the homogenization of the CO2, but also you can get the composition of the water, making the freezing point of the water. We will talk about how the microthermometry works. So, and this is petroleum. So you have some hydrocarbons inside, and fluorescence is a good way to see the presence of hydrocarbons inside the inclusions. And it is very important if you have the combination, for example, of fluid inclusion, having water and having hydrocarbons inside. Because generally, also if they were born, let's say, were formed at the same time, they will have different homogenization temperature. And you can get the intersection of the homogenization temperature of the isocores, which are the place of iso density of the fluid. You get the intersection of the isocore from water-rich inclusion and hydrocarbon-rich inclusion, and the intersection between the two lines give you precisely the PT condition of trapping of your fluid. And this is very interesting. Okay, you can have also melt inclusion, and this is something that in a volcanic environment is very well known. And so you can get inclusion of different melts or the original melt molten material inside the crystals. And of course, to perform microthermometry with this kind of inclusion, you need a particular stage that can rise up the temperature to get again the molten material inside the crystal. How you can have multi-phase inclusion? So you see different crystals, different crystals here of different materials where the composition is quite complicated. Now, one question, of course, is what is better to do? Is it better to study primary, secondary? What we should measure? It depends on what is the geological question you want to answer to. And in fact, as I said at the beginning, you have to have a question. What you want to know from fluid inclusion. So having in your mind what you want to know, you study better which kind of inclusion you want to measure. In some cases, secondary inclusion can be very important, in particular when you want to have a history of exhumation, for example, in an area, and you get several brittle events. You can study the intersection between the fractures, so you can get the feeling of older or younger fracture, And so you can study several fluid inclusion assemblages relative to your fracture and see if the fluid was changing. Okay, this is again a very complicated stuff, but this is also to ask what you want to measure. So what is this? This is a schematic imaging from Bodnar, another great father of fluid inclusion. I was very lucky to study in his lab for a couple of times at the Virginia Tech, and he is still one of the best in the world for fluid inclusion studies. And he wrote a lot of papers and books and so on. So this schematic stuff is to see that you can have really several groups of fluid inclusion. For example, in this picture, what do you think? Which are the lateral inclusion you form in this assemblage of crystals and stuff? Which one can be the very last one? Yeah, around this fracture, you know, this is a fracture, a field fracture that cut through everything. So for sure, they were formed at the end of the evolution of this stuff. And then you have cement here between grains. This is a sandstone. And so you get some inclusion into the grain of the sandstone. That can be very old. Probably they belong to the original rock, but gave rise to the grains of the sandstone. Then you have the cement, you have different inclusion into the cement. So you have several stuff, different stuff inside the grains. So this is why I said you have to have a question. Do you want to know where the grain of the sun or the sandstone comes from? Okay, you have to look at these kind of materials. Do you want to know something about the sedimentary environment? You have to go to the cement to know what was going on in the sedimentary environment. And if you want to know about the formation of this stuff, go to the fractures and look at the fluid inclusion, secondary fluid inclusion, okay? If you want to know everything, you have to measure everything, of course. Okay, and this is the list of the different, what is this? Oh, no, sorry, I made a mistake. I made a mistake. Okay. Sorry. Okay. Yeah, because there is this stuff here that I don't know what is it. Anyway. You don't see, yes, this is, what is it? You don't know. No, but I think. So perhaps it's too much to go into each detail, but anyway, they have been measured and classified with respect to the content and the behavior of the inclusion. So you have these several groups. So finally, the FIA, the fluid inclusion assemblies, represent the smallest temporal resolution possible to constrain inclusion tracking. So you have to distinguish fluid inclusion assemblages that can be useful for your purposes, and you go to them. Okay, is it clear to everybody? So I already mentioned about the the sample preparation, but sample selection, of course, sample selection happens in the field, first of all. So you want to know precisely what you are sampling, and because you have your question into your mind, and you go to sample what you need. For example, if you are looking to fault evolutions, you will go to fractures related to the fault damage zone, or to the fibers, crystal fibers along fault plane, and so on. So you will select in the field what you need, and then the important thing is the polishing of your sample. So you have to cut the sample and very nicely polish the sample on both sides. So you will polish one side, then you glue into your glass with a reversible glue, so something that can be dissolved into acetone, okay? Because later on you need to take off your sample and then you polish nicely the second stage. So it has to be really a fine polishing to make it very well transparent and to give you the possibility to glue through this thickness of 150 or 200 microns. Then you need a good petrographic optical microscope. You will choose your fluid inclusion assemblages, and you will have also photographs and draw of your inclusion. You see down here, this is a draw made in the lab while you were studying and watching the inclusion, and you get the feeling what you're looking at, you make your notes and your consideration while you are measuring. Okay, let's go through microthermometry, which is what you can do in your lab here with your Lincoln stage. And I have done both many years ago with the Lincoln stage, but mainly in my lab in Camerino, which has an old style stuff, very nice, but quite old at the moment. Very nice, it is all manual, and I will show you some images of the lab. And but it is very precise anyway. So what you are going to do with your sample? First of all, the petrographic analysis, and we have done together to see the assemblages, primary, secondary, pseudo-secondary, and so on. Then, when you want to measure the phase changes into the inclusion, you have to take off your sample to break the sample and take the best pieces you saw during the petrographic analysis. This is very difficult because you often lose your sample because you don't break very well or something is broken. And but anyway, you try to do the best because you need little chips, little pieces to put into the chamber to be measured. And you can do two things, the heating cycle, so you blow up the temperature, rise the temperature, to get the homogenization temperature, which is the temperature where you will see the bubble disappear. And so you get one unique fluid into your inclusion. What it means that you go back to the initial situation, because when the inclusion was trapped, it was one phase inclusion, and the bubble developed during the cooling down of the system, and so the volume of your fluid, which into this capsule, started to shrink, and you develop the vapor bubble. So if you go back and you make the bubble disappear, you get the initial situation. All liquid or all bubble, it depends. And this is an interesting measurement because it gives you the minimum trapping temperature estimation. So you go back to the initial situation, and so you have a feeling of what was the trapping temperature. This is something very fascinating to me. So I was studying, thinking to these, and it was amazing in my mind. I mean, more than the cooling cycle, which is also very important, of course. So the cooling cycle freeze your inclusion, and then you rise up the temperature till you see the last ice crystal to melt. And the ice melting temperature, or the objective temperature, is depending on the salinity of your fluid, and give you an estimation of the salinity, so of the fluid composition. Generally, we make consideration, I will tell you later, about an approximate salinity. So we compare the salinity to NaCl weight percent system. And then you check with other techniques, you check the precise composition. You cannot check the precise composition with microthermometer. So the phase transition can give you important information. Of course, some changes can happen during the storage of your system. So what you have to check is that these changes didn't happen. What I mean, I'm going to the, sorry, okay, to the so-called radar rules, because many times you manage with old materials, very old materials with a lot of history of this deformation, exhumation, and or history of geothermal different events and so on, metamorphism. So you need to check that you didn't have too strong changes into your inclusion that make the significance of inclusion not really important. So they change the condition. So first of all, you have to suppose that the inclusion was trapped in a single homogeneous phase. Because if you have many phases during the trapping, you can have different proportion of your fluid into different inclusion. What I mean? I mean that one inclusion can trap all volatiles, one another to the in the side, just liquid and so on. And so you will get different density of your inclusion. And if you make the microthermometry of this inclusion, you will get many different results. You don't have an homogenization temperature in a narrow range that can give you an information. You have a rubbish anyway. So you can measure inclusion if you are confident that they were trapped in an homogeneous single phase. Then another assumption is that the volume of the inclusion has not changed since the entrapment. And this means that the inclusion represents an hydrochloric system. So also, for example, if the inclusion was formed at many kilometers at depth, and then it was exhumed, the exhumation has to be slow enough to follow an isochronic path. So the balance between pressure and temperature has to be quite narrow to make the inclusion stay on the isochore, which is the line of isodensity. Because if you go very much out of this situation, you can get deformation of your inclusion, so the volume will change, and as a consequence, the density will change, and you get results which are not the original results. So you will get a density and homogenization temperature which doesn't tell you the initial condition. Also, you have to check if there is no metastability during measurements, and this always very often can happen. So many times you have to recycle the measurement till you avoid the metastability, because metastability gives you wrong results, of course. So you go above the temperature you expect. Simple because, for example, the bubble does not nucleate, because there is this condition of metastability. And then, of course, you have to know the phase equilibrium for the system under consideration. So you need the composition of your inclusion with the method that you mentioned, for example, the cooling cycle of the inclusion. Are you tired? Can you follow the thinking? Yes. Okay. So let's have a look very quickly to my old style laboratory, where you have the facilities, mainly the microscope, of course. This is a big tank of nitrogen, and this is the compressed air that is needed to refresh the system. And on the other side, you have on this side, you have the control for temperature, and you have a monitor and everything. So what you see here under the microscope is a stage, come si dice, refractario, so insulating the temperature with the material that, come? And okay, these are the details. So all this stuff is to maintain the temperature constant, not with the influence of the environment. This is a thermocouple which goes into this little chamber where the chips of the sample is placed, and it measures the temperature, different temperature. Now, this is how the little chamber is made, and this machine was handmade by a researcher in the US, which is called Reynolds, who sells his stuff all over the world and many laboratories for tens of years, use mainly this stuff. And so this is the draw of the little chamber where the sample is. And here is the specimen, the sample. All these you see are glasses, very thin glasses. You have seven, 3 above and 4 below, 7 glasses, and the air flows through the glasses to avoid convection inside the chamber, and to maintain a constant temperature in all the environment, in order not have changing in temperature in different positions. So to make sure that your temperature, the one which is recorded by the thermocouple, is that, no variation inside the chamber. So very complicated stuff, and you measure, and sometimes when you go to high temperature, you break the glass, you have to change with the, come si dice, quei cacciaviti? Tornillo? Okay, you have to change the glasses, go back, so it's a lot of work, but anyway, amazing. Now let's go to, this is not yours, this is from Martina Zuppi lab in University of Bari, but it's the same stuff you have in your lab. So it is the income stage, which is much more evolved and much more automatically controlled. So you have a software inside, so you have the controls about the measurement, the rate of heating or cooling, and so on. And again, you have a good monitor to see the binocular and the stuff for making photographs. This is the nitrogen, the temperature controller, the liquid nitrogen pump to send the nitrogen inside the chamber, and so on. And I think there is, I don't know if it is here, there is a little moving on the preparation of the stuff, just to see where the sample is. I don't know. With the light, we don't see very well. Do you see anything? Yeah. So you have the sample inside here. This is the light from the microscope. You close with this steel cover, and then you close up with another, because also here you have to preserve from the outside environment to see. But just this one first. Basta che queste più avanti. No, penso qua. No, this is the room. È spento la sala, devi spegnere il... No, hai spento il Mi riposo.
Hacemos una pausa. Pausa caffè. Una pausa. Una pausa.
Allora, fa. No, sono uscita anche.
Hola, hola. Hola, hola,
Prima
hola.
l'ho spento perché sennò faceva...
Está apagado.
Ah, è spento adesso però. Pronto, pronto.
No.
Hai fatto un casino, Ruben. Dove è finita la... Oh.
Però questa cosa non ricordo da basso non intervento, non è caro. Sulla preparazione.
Allora, la preparazione, sì, c'è un bravo tecnico per le sezioni sottili. Mm. La preparazione è un normale laboratorio di preparazione di sezioni sottili, però con l'accortezza di lucidare molto bene, perché queste non si possono coprire col vetro, no? Devono rimanere... quella è una roba manuale. Cioè, sei te che devi essere bravo a non mandare tutto a schifio e questi pezzettini li metti. Quello che costa di più è questa apparecchiatura qui. Questa
No,
sì.
comprarla e tutto, però una volta che sta installato il costo.
Il costo è il costo dell'azoto liquido, a noi serviva poi l'azoto industriale perché, ma credo che voi non so se ce l'avete direttamente, io nel laboratorio non c'avevo il vicino del gas, insomma, no? E quindi dovevo comprare le bombole, quindi sono i costi vivi del materiale di consumo che è azoto, azoto industriale gassoso e azoto liquido. Se no, altre spese, a parte la preparazione dei campioni, non ce ne sono. Sì, sì, esatto. Basta che-
Hola, hola, hola. Hola, hola, hola. Sì.
Forse è perché abbiamo spento la luce. Mannaggia, mi è venuto il raspino. Ah, pagamos una que ¿verdad?
Hola, 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 hola. Hola, 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 hola.
Ma sarà qui che devo attivare questo, no? Claudio,
Forse-
sì. Provo a attivare questo.
No, porque el sonido no. A ver. Hola, 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 hola.
No, es acá. Attento il figlio, che non ha attento figli. Figli per te.
Ahí va. Sí, sí, todo bien, todo bien. Ahí estamos, ¿qué? Perfecto.
¿Ah?
Listo, Chiara.
Gracias.
Continúa.
Bueno. Vogliamo continuare? So, you have seen this little movie, but just to see some parts of the equipment. Now, this is a 3D diagram, just to imagine the trapping of an inclusion. So this is a pressure, temperature, density diagram. So you can imagine to trap an inclusion in this position, A here, at a certain P3 condition. And then gradually you cool down the system because of exhalation or because simply it cools down naturally. But yeah, because of exhalation, in this case, you are dropping down the pressure. So you move from A to B, you are along the line, which is an isochord. So you trap the fluid in a certain condition, and it has a certain density. And if you move along the isodensity line, which is the isochord, the density doesn't vary inside this system. Why? Because if you crystallize the crystal and you have this pocket inside the crystal, if you cool down, the crystal doesn't change very much. And the pocket entrains the fluid, but the fluid gradually changes, not its density, but its attitude. So, for example, when you cross the liquid bubble surface here, this surface, you start to develop a little bubble because your fluid is shrinking, but you have always the same space at your disposition. So you reduce your fluid because the excitation of the particles, they are not more so excited, let's say. So they slow down and you make enough space to develop the bubble phase. And so when you cross this surface, you start to develop the bubble and you go down, down, down below the liquid bubble surface, and you get a larger bubble at a certain point, which is the equilibrium for that fluid. So now, at this position F, for example, the density is the same. So your fluid, because it moved along this line, your fluid didn't change density, but you developed the bubble, because the PT condition are different from the trapping condition. So, is it clear for everybody? Some doubts about this? Someone didn't think very well. So you trap an homogeneous fluid at a certain pressure, temperature, and condition. For example, you are in a metamorphic environment, and some fluids are trapped during the growing of crystals in a vein. And then you exceed this system gradually because of normal faulting or something like that. So your rock that were 15 kilometers at depth now rise up. If you rise up quite slowly, you maintain the equilibrium, you move your fluid along this isochoric line, which is the line of the same density. So your capsule doesn't change volume, and the density of your fluid is maintained. But because of the new condition, because of the drop in temperature, you develop the bubble because your fluid shrinks and you have space to develop the bubble phase. And so again, this F situation is the same of A, just in a different pressure temperature condition. Okay. So what you do in your lab is going back. So you see this at room temperature, and then you make the heating cycle with your machine. And so you go back, you shrink your bubble till it disappears, and this will be the TH, homogenization temperature. And you record it because it is very important. And as I said, it is the minimum trapping temperature. Why the minimum trapping temperature? Because it is a real trapping temperature in diagenetic condition, when you don't have very much correction for the pressure. But in a diagram I show you, these are the diagrams, for example, of the isochords, PT diagram for NaClH2O system. So these are the iso-TH homogenization temperature line for this system, having different salinities. So thanks to Bob Bodnar in 1993, he developed an equation that made it possible to calculate all these graphs for different percentage of NaCl equivalent fluids, NaCl equivalent dissolved into the fluid. And so these are the graphs for all the isochores at different percentage, 5%, 10%, oh, this is 10, 15, oh, this is 0, pure water, 5, 10, 15, 20, 25, and then there is also about the authentic composition, other graphs, because here you have liquid plus hydrohalide, because it's very salty solution. And so, if you chart, for example, your fluid at a certain pressure, temperature condition, let's say 3 kilobar and 300 temperature, what you will record in your lab is 200 degrees. So you will be along this isochore. So you will get an homogenization temperature of 200 degrees, but you don't know really in which position along this line your fluid was trapped. So besides you are in a diagenetic system, and so your pressure won't be very much higher, and your condition of homogenization are really close to the trapping temperature. You can have 10, 20 degrees of shift, but you can say that your homogenization temperature is the trapping temperature in diagenetic condition. When you are in metamorphic condition, for example, you need some independent way to say something about pressure, because you don't know if you get 200 degrees Celsius homogenization temperature, you don't know that if your fluid infusion was trapped at 2 kilobars, 4, 5 kilobars. And you see, when you go down here, if you trap at 2 kilobar, you get 250. If you trap at 4, you get 300 degrees trapping temperature, okay? Because the isochores are inclined. So you need an independent way. This is why I told you before that one powerful situation is when you have different fluid inclusion composition. For example, the ones with hydrocarbons together with the water-rich inclusion, because you can get the cross position of two different isochores, one for the NaCl H2O composition and another one for the hydrocarbons, and you intersect the two isochores and you get a precise point in the PT diagram. So these are the diagrams, as I said. Sorry, I had the yes, I had the graphs. I didn't remember about this. So you get the pressure trapping thanks to the two isochores. This is the isochore for the hydrocarbon, and this is the isochore for the NaCl system, aqueous isochore. So for example, you get a kind of an homogenization temperature for the hydrocarbon, and then a homogenization temperature along this isochore for your water-rich inclusion. You draw, thanks to the software, so you draw the two isochores and you get this intersection. And these are the PT condition of trapping. So you can precisely say trapping temperature and trapping pressure. Okay? But you are not very often so lucky. So generally, for example, when you work with metamorphic flow, you use the petrographic pages to say something about the pressure condition. So you know, we do the petrography mainly. Now this is going through several images. This is what happened during the heating cycle in a nice case. So I show you a very nice inclusion that is very easy to check. Okay, so you start from this situation. You see it's a kind of room temperature, 26.4 degrees, and then you increase the temperature, 150, 210, you see that the bubble becomes tiny and tiny, till it is almost disappeared, but it is still there, 235 degrees. So you need the moment where it completely disappears, and at that time you stop the temperature, come si chiama, il contatore, the counting temperature, and at 235.4, you get the disappearance, complete disappearance of the bubble, and this is your homogenization parameter. Okay? Yeah.
Yeah. You saw your software.
You know, it's visual. You have to be good and watch. Yeah, I don't know if the Lincoln has any facility about this, but I don't think so. I will ask Chino, but I'm not sure. I think you always have to check. It's a visual check. Okay? And in fact, many times you need to go back and forward. So you think this is your disappearance point, but you are not completely sure. So you slightly go back with the temperature. As if the bubble suddenly reappears, it was not homogenized. It is homogenized if you go back 20, 30 degrees before the bubble reappears, because you get a kind of metastability. And so if you homogenize before you get the appearance again of the bubble, you have to go back at least 20, 30 degrees. And you will see the bubble reappear suddenly, not so tiny, perhaps this position or this, because you went back with the temperature. So you have to cycle a little bit with the thermocouple, going back and forward to be sure that the bubble will disappear. So this is the homogenization. And when you are close to the end, this bubble got crazy. So it started to go around into the into the inclusion because it's metastable, you know, and so it goes around everywhere. So sometimes it's difficult to check when it disappears. Yeah. So yeah, that in that condition you should have something else, but you don't. So for example, if you want to freeze your, let's go to the freezing point. So okay. These are the examples for freezing your inclusion. Is a water-rich inclusion again, is the same. So you see, nothing happens till minus 30 degrees. So this is metastability, because you should have ice inside here. You should have ice, but ice didn't nucleate yet. It nucleates suddenly at minus 50. So this is because you are changing quite fastly the temperature into your machine. And so the system needs time to rework itself and to put in the right position. And so you go down till minus 50 before getting everything frost and nucleate your ice crystal. If you stay at minus 30 for a long while, probably you get your you get your ice, yeah. But during the running, generally you go down until you get the ice, not gradually. You don't need to go gradually, because what you want to see is the melting point, not the freezing point. So you need to make everything frost, like in this position. What you notice? You notice the crystals, and you notice a little shrink of the bubble, because of course ice has a larger volume than water, and so it reduces the volume of the bubble. Okay, and then what you do is heating out. And during the heating, you continuously change the shape of your ice crystals, and depending also on the salinity of your fluid, you get flat rays sometimes, so highlight and water crystals together that generally grow around the bubble. And so you see, you change your crystal in this position, minus 11, you have ice crystal and some liquid, but still ice crystal, and when the last ice crystal disappears, you have your ice melting point. This is minus 6.3. Of course, as perhaps you know, when you have a saline water, the freezing point is depressed, so it goes under zero. So in this case, minus 6.3 means that you have NaCl equivalent solution into your water. I think there is a movie here. So fluid inclusion containing gases for solution not saturated at room temperature. So the composition can be estimated thanks to ice melting temperature, looking at the last solid to melt. So what we see here, you don't see the temperature. I read from my monitor is 22 degrees, so it's room temperature. Now we are minus 27, 29, 30, minus 32, and you see that you start to change something because ice is forming, but not everything is already frost. Now it is, you see? Have you seen the change? You want to go back to see it again? Let's go back. Okay. Look carefully. You have a slight string of the bubble, and yeah. Now, have you seen? Okay, everything is frost now. You are minus 55 degrees, 57. So you have to be sure that everything is frost. Now, when you're rising the temperature, minus 12, everything is frost here. But you start to see some changes in the material, in the ice. They change, minus 4. Yeah, it's changing, it's dissolving, not everything. You see, you start to move the bubble and the crystals. Yes. Yeah, minus 3.3, I think, was the melting temperature of this fluid inclusion. So minus 3.3 means a certain salinity. So the percentage of NaCl equivalent expressed in weight percentage of NaCl equivalent gives the composition. Okay, this is a table. So minus 3.3 means 5.41 NaCl weight percent equivalent. So this is the salinity of your inclusion. This thanks to Bodnar equation. I thought I wrote the equation here, but perhaps I didn't. Yesterday I added, but perhaps I didn't say, I don't know. But it's a simple equation you can find online and in the books, because now it's something consolidated. And so this is the table for all the different, depression of the freezing point here on the left, 0.1, 2, 3, 4, and you have the percentage till the eutectic percentage, because afterward you start to have ice crystals, highlight crystals into your bubble. So you will have 3 phase inclusion: liquid plus bubble plus crystal of halite into the salt into your inclusion. So let me see. This is probably another movie, or is the same? I don't remember. No, it is the same. Okay. Oh yes, sorry, it is the same one. Okay. So I mentioned before the necessity to have an isochronic path. Otherwise, you can change the density of your ingredient. For example, let's imagine a very fast exhumation of bonds. So you produce veins and with glowing crystals inside at, let's say, 8 kilobars pressure and 300-400 degree temperature. If due to some tectonic accident, you have a very fast exhalation, what happens to your inclusion? So you got this high pressure inside the inclusion, while the surrounding goes to much lower pressure in a fast, geological fast way. So your inclusion is over pressure. So it depends on the mineral who hosts your inclusion, if the inclusion can survive or not. For example, if it is calcite, which is quite soft mineral, and you have this overpressure inside the inclusion, you tend to explode the inclusion. And so you don't preserve your fluid, you cannot do anything. I will show you an example about this. Or, in the best way, for example, you have quartz, you don't explode the inclusion, but you can produce leakage, which is microfractures along which some of the fluids go away, and so you change the density. And when you go to measure the homogenization temperature, you don't measure the original homogenization temperature, but you measure the homogenization temperature of a fluid which is different from the original. So perhaps you get a different temperature. Or simply you change the volume of your inclusion because it is deformed. Okay. So this is what is shown, for example, in this position. You change from one isotope, you shift from one isotope to another due to kind of process that may changes in your inclusion, and it is not more as it was at the beginning. You can also have something different. If you have microfractures and leakage of the original fluid, some other fluid can go inside. So, for example, you entrapped fluid from a metamorphic condition, original fluid of the metamorphic condition due to dehydration or decarbonization, decarbonation of minerals and so on. Then you have an uplift and this leakage, and new meteoric water can circulate in the environment and can refill your inclusion. So you have to pay very much attention in the petrographic analysis at the beginning to avoid the presence of microfractures, of leakage, of other processes, and of these kind of processes, for example. You can trap your, let's imagine this is a fracture. And at the beginning you have a large inclusion like this one, or several large inclusions, while you are healing your fracture. But the inclusion, the fluid was homogeneous. So you start to get smaller and smaller inclusion while your fracture is healing. And at the end, you will develop at room temperature small bubbles, all equal, because the fluid was homogeneous at the beginning, and then at the end, you have the same percentage of bubbles in all your inclusion. Let's go this way. So you start to cool down your system or depressurize your system. You develop the bubble. So you develop a bubble phase, and then you start to form smaller inclusion. The fracture starts to be healed. At this point, for example, you can have that the bubble is entrapped just in one, and the other two are still liquid. And then you go down with the temperature, they develop the bubble, but you see the percentage of bubble in this inclusion is not constant because the immiscibility, the two phases were already present while this stuff was forming, this small inclusion were forming. So at the end, you will have a fluid inclusion assembly, which seems to be homogeneous, but if you check carefully, you will see that the percentage of bubble is variable in the different inclusions. So you cannot use this data to say, okay, this is my homogenization temperature, because you will get a distribution of homogenization temperature over a wide range, which is not a confident data. Okay. This is a kind of necking down. So you have, in this case, the necking down is in this bridge, you're reducing two different inclusions. These two are homogeneous. These two not, because you have a lot of bubble here, no bubble in this other one. Okay? So you can check during the petrographic analysis if there are phenomena of leakage, microfracturing, necking down, and so on. This is very important. Very nice. This is a, I don't remember in which sample, it is in quartz, but I know, I don't remember where I took this picture. Now, how to check if there was leakage, for example, or if there was stretching, so changing volume of your inclusion. You have a system because sometimes you are not sure. Perhaps your petrographic analysis was not enough to distinguish if there was some of this process. So you go to measure your inclusion, and then you can make this kind of diagram, putting together melting, temperature of ice melting and homogenization temperature. If your measurement go to be distributed along a line like this, it means that the fluid was changing. And so you get leakage and refill of your inclusion. While if you simply change the density of your inclusion because of stretching of your capsule during the geological event, you will get measurement aligned along this, along a path like this, which means stretching. And so you know that your measure and to be taken much care. So perhaps you need other measurements, you need to see another sample and something like that. And these are some examples of wood stuff, group 1, group 2, you see EM, ice, melting ice, homogenization temperature. You have two groups, but they are very close, they are clustered, so these are good measurements. These are different groups, not very good, but still possible. This is good, these are good, three different groups in different conditions. And these are the two I showed before, so where you have a leakage or stretching of your samples. So, till now, I talked about the microthermometer. So all the petrographic analysis that we need, and then the changes in temperature we can perform under the stage, the microthermometric stage to watch melting point or homogenization point. So the cooling cycle and the heating cycle. And you've seen that we can get some information. So the homogenization can give some information about the trapping temperature with some correction if we are at high pressure. And the melting point can give information about the composition. Can we do something else? Yeah, there are many other techniques that can be applied to get more information about the fluid that is in fact, so they can help in giving information on the environment during the trapping and so on. And these are some of the possibilities. I think you have Raman spectroscopy here. Not here, but in another department. Yeah, okay. In the city. Okay. Okay. And for laser ablation, I see PMS spectroscopy or SEM analysis. You can get different information. For example, with Raman, you can check if there is something else besides NaCl in your inclusion, and thanks to the diagrams, you can get tips for different composition, different elements which are present in your inclusion. Okay, these are examples. And this is a non-destructive analysis. So it means that your inclusion is preserved. So if you want to measure again later on, you can do it. But with this laser beam, you can check the composition. While a destructive technique is the laser ablation, so make sure that you made all the measurements you need, and then you can use your sample for laser ablation to define the concentration of chemical elements. I'm not expert about all these techniques because I just used once, I think, or a couple of times the Raman, which used by a technician expert on this. So I was a spectator of the situation, in fact. I never use laser ablation, but it's important to know single elements, you know, the percentage of the single elements present inside the inclusion. And also the SEM, you can detect with the microprobe, detect the different phase presence of the different elements present into the inclusion. So I think that this is, yeah. Okay, these are other examples when we already mentioned about what isotope are. They are lines connecting equal to the volume of density in the PT coordinates. And so this is the example for water. The PHH is the homogenization of hydrohalite. When you have high density solution. And again, this is the homogenization of an inclusion and the description of the graph. So the isotope, the liquid, the vapor, the surface liquid vapor curve, the trapping temperature, how can you move along the isotope, and some independent information for the pressure. So you get the trapping pressure and as a consequence the trapping temperature. Okay,
Sí. ¿Dónde lees ahí en la intersección entre la curva roja y la isomora? Ahí lees la expresión de temperatura que está marcada arriba.
qui dici?
Claro.
Qua.
¿Cuál es la condición de?
Allora, in this case you had and you measure the homogenization temperature,
Yeah.
this one. So you are in this position on the liquid vapor curve, your vapor disappears, and so you are along this isotope.
Yeah.
Okay? To get this point, you need an independent information about pressure. Okay? So you have another set of inclusion that can intersect with this isotope, or you have a petrographic analysis. This in the case of metamorphic rock, you have the petrographic phases, and you get the trapping temperature here. So you measure homogenization about 300 degrees, but your real trapping was about 500, 400.
Se formó la inclusión en trapping temperature.
Sì, trapping temperature è quando si formò l'inclusione. Okay.
No me queda claro cómo obtenemos información de la presión de la superficie con otras inclusiones, aparte si es metamórfico o fácil metamórfico.
Sì, con altre inclusioni.
¿Cómo,
Sì, se hai delle inclusioni con composizione differente. Per cui, per esempio, il caso che facevo prima, sì, the case I made before, when you have together aqueous inclusion and hydrocarbon inclusion, you will get a different homogenization temperature for the two and different isocores because, for example, the H2O isocores are very steep. The system for hydrocarbons has more gentle curves. So you intersect these two curves and you get the pressure as a consequence.
Hydrothermal system. Thermal, whatever. What can we do? What can we do? You don't have any kind of information, metamorphic
generally, you go with the geological reconstruction. For example, I will show you an example in Isola d'Elba in Italy, where the pressure was deduced from the geology. So the knap pile of trap, the thickness of the lithological naps, and so you get your information about pressure because you know that you have a thrust pile of 2 kilometers, 3 kilometers, and so on, and you confine your pressure in this way. So knowing the geology, you need an information from an independent information about pressure that you can have for the start pressure. Okay. So I think this is okay. These are okay. These are some example of the ranges where you found your inclusion, the ranges in which you calculate looking at different colors are different groups of inclusion, so you try to confine the range of PT condition at which your inclusion were formed. And I don't know very much about this diagram because it's not by me, this is by Martina Zucchi, but anyway, in this case, you have the phase equilibrium for the inclusions, which are the colored one, and analysis field. So you have the equilibrium for the analysis, and you get the intersection between the two, and you can make a range for the existence of the tracking position for your inclusion. This is static pressure, you see? So it's reconstruction that has been made by geology, by regional geology. Now, if you like, we can spend a few minutes to see some couple of movies. Allora, interrompo un attimo la condivisione. Because I need to no, però adesso devo riprendere la condivisione. Come si fa? Così. Facciamo così. Dunque. Dove? Ma dov'è? Non lo trovo più. Ah, sì, ok. Condivido schermo. E in questo caso faccio schermo, desktop. Ok, ok. Here. So this is easy for everyone. You can go to check. There are several movies. This is from Lille University in France. And there are several informations about fluid inclusions. So let's have a look at this one, which is the water system, pure water. This. Come?
Quello nero lì, guarda il
Questo?
sì, e poi
I hope it works. So you see the inclusion here, which is water inclusion. So these are the water vapor, the meniscus. And now we are going down with the temperature, -1, -13, 15. You see, this is the metastability because it should be frost, but it's not. And going down and down, and you will see again the shrinking of the, okay. Perhaps you appreciate the shrinking of the bubble. And everything is frost. Now we rise with the temperature -2.2. You see that the ice is changing continuously. -1.3. This should be full water. -0.8, 0.7. You see that the ice is disappearing. -0.3, we go down slowly. gone, so everything was molten at 0 degrees, okay, so pure water. So, let me see if I can reduce. Come si sta? Ah, bravo, grazie. So this is, you know, the diagram of pure water. So what we have seen, these are the conditions. Number one, at room temperature 25 degrees. So we went down along the liquid vapor phase, and at this point, everything should be 0 degrees, should be frost. But in fact, we went down here in a metastability field where ice was not yet produced, and then suddenly we dropped down along this sublimation, let's say, going between vapor and ice. So we dropped down after the metastability at around -30, I don't remember, 35 degrees. So we drop along this, and we have the bubble and the ice. And then we go back, rise the temperature. We go back here till all the triple point, all the ice was frost at 0 degrees, and we go back. And measuring this point where the last ice was melting, you have the composition. In this case, it was 0 degrees, so pure water. Okay, so this is very nice. Go to this site for probably university, because you have all the diagrams. It's really nice. I want to show you CO2, which is also interesting. Because you have a double meniscus in this case. You have the bubble CO2, liquid CO2, and liquid water. Now you go around the sample looking for a good inclusion to see, to watch at. And at the end, they choose one. And we are at room temperature 14 degrees. Okay. This is our inclusion. For dark, this is the bubble. Again, when you homogenize the, this is, I think it's pure, sorry, it's pure CO2. You don't have water. So you have a liquid and bubble CO2 going down and down. It's pure CO2. -50, -60. You see that something is changing. 74, then it will become very dark, -80. And again, we homogenize. Okay, now everything is solid, okay? So you go back, -59, and to be sure that it is pure CO2, you should have the melting at -56.40. And in fact, you are melting. -57. Not yet completed. 66.6 finally. Have you seen? Okay. So back to the initial condition, and you check the temperature, and this is precisely the temperature of melting, which is expected for pure CO2. And in fact, this is one of the calibration points for the machine, for example, or calibrate the machine at low temperature, we use pure CO2 sample. And now you are growing the temperature above 0 degrees, 17, and you go to the bubble condition. So you are homogenized to the, no, sorry, I think to the liquid condition. Yeah. So you see the bubble is tiny, and then disappeared at 17.8.9. And this is also a point to say the composition. So let's go to the diagram. So we moved from the tracking down to the triple point, and then again in a metastability field -96, and then we went back. We had the the solid here, of course, solid till minus 56, where you have the triple point, and then you went up with the temperature, and you got this temperature here, where the bubble disappeared, and you go in all liquid tea. So you move around this isotope, which is the isotope for the CO2, pure CO2, or 0.85% of CO2. So the bubble disappeared. You see the tiny bubble that disappeared, and you went into the pure liquid field. So all the fluid inclusion was liquid. Do you want to see more? Or you want to stop now? Or you go to check that yourself? Some music? Che dici?
Check the composition of the leaf, and then playing with the melt,
Yeah, I mean, of course, you can have inclusion. I show you in the presentation mainly solution of the CO2 and ACL to make the thinking. But of course, you can have different things in your inclusion. So this was an example of full CO2, but you can have combination of CO2 and water, for example. I don't know. This is no. There is no this one, complex mixture. That's this one. Okay. And so you can appreciate the water gas system, for example, and you can produce clay and so on. You see, you have a double meniscus here because you have both liquid water, vapor CO2 and liquid CO2. You see, very nice. So these are complicated composition, and you can measure the different, the homogenization temperature for CO2 and for water. Okay, they choose one here. This is room temperature. Nothing happened. Okay, minus 20 degrees. It's going down slowly now. You can put your rate of temperature, how fast you want to go up and down. Sometimes you have at first, okay, now, I think it's finished. Oh no, sorry, I stopped. So you see, now you develop ice in this position here. So in the liquid water now it's frost. You have an ice crystals, while there's still the CO2. And then going down, you will have an homogenization inside the CO2, probably. I don't remember about this movie, but yeah. Okay, so now it's a solid, also the CO2. And then you go back, and so you see if it which kind of CO2, perfect, 55, minus 55.6, so this is CO2, definitely. And then you rise up. So they were not interested in the melting point of the water. So they jumped to the above the 0 degree temperature. I don't know why, but you could also check the composition of the water in this case. Minus, let's go back again. First we check. No. Okay, but it was nice to see the two passages. So when you get ice and then you get solid CO2, and then you can go back and see the melting of CO2, and then also the melting of ice. And you are changing inside here. Yeah, now probably the melting of ice with some metastability is above 0. I don't know. Okay, I think it's finished. Oh no, it's going on. But I don't remember what they are checking here. We should breathe into the nose. Yeah, probably, sorry. They were checking about some some crystals still present above 0 degree. So nothing CO2 class. Sorry, the clutterate formation. This is why we continuously saw movements inside inside the inclusion, because there was clutterate formation. So this mix of CO2 and water and NaCl that produce crystals continuously changing, and in the inclusion. So you see continually some movement because you have clutterate formation also above 0 degree. Okay. Solidification, okay, yeah, it's an observation about clutterate which are forming and dissolving, which means also that did you find something? Did you find another movie? No, sorry, I thought division of the clutterate. So this is because the movie is going on again some more, because they are looking at the clutterate. Okay, so of course, yeah, this is the description with the clutterate that continuously form. That's very nice, because you have all the description of what happens at different temperature inside the inclusion. Okay, so I think that I can stop here the first part of the seminar. I mean, the description of what happens with food inclusion, what you can do with food inclusion, and what can be performed in a macrothermometric lab with the cooling and heating of inclusion and so on. And now the second part is with few case history. I don't know if you want to start now. Yeah, okay. Oh. So, as I said at the beginning, when we approach the study of food inclusion, we want to know how to use it and why we want to use them. So let's go inside the possible solution of some geological problems. And these cases come from some studies that I performed years ago, because in fact, it is about 8 years I'm not working on food inclusion at the moment, but we have several cases. I just put some of them, of course. So as we said, the food inclusion can contribute to solve questions about food circulation variation and the consequences, or environmental variation during progressive deformation, for example. Of course, I was particularly interested in structural geology problems, or in the PT path reconstruction, prograde and retrograde. And I have an example of these. The last example I will show you, the fourth example, is not by me, it's by Martina Zucchi in the Isola d'Elba, and I will show you. So this is Italy, and for those of you that don't know, and of course, you know, we have two main mountain chains, the Alps, in the northern part, and the Apennines, which goes through all the peninsula. And these squares that you see here are the areas where the study I will show you were performed. So this is close to my house and to Matteo's house. Matteo lives here in Senigallia by the Adriatic Sea, and I used to live there because I have my mom there. It's my hometown. But then I moved to Camerino. I studied in Camerino. I found my husband in Camerino dramatically, so I live in Camerino. And so I moved for my research, for my study around, my doctoral, my PhD was in Perugia, and then, as I mentioned at the beginning, I worked abroad several times. So this area here, I will show you more in detail, is close to Camerino and southward, going toward L'Aquila and so on, and is affected by strong earthquakes. Then two areas in the southern Italy. The first one is between Campania and Basilicata, two regions here. It's about deformation, progressive deformation, this study. This one is about metamorphic rocks in a subduction zone of Neolithic rocks in Calabria, Diamante place, and the final one at the Isola d'Elba by Martinazzo, as I mentioned. So, the first example is about the fluid circulation variation and some evidences that we were able to show in a seismogenic area. So we are looking at quaternary faults in the central Apennine. It is called CAS, Central Apennine Fault System, and is responsible for the earthquakes. Now, this is an old work, and it was performed after the earthquake that affected the area, the Cortolito area in 1997. Then we had another strong earthquake in 2016, which was stronger and made much more damages. And I am out of my house myself from that time. So anyway, the study that I performed after the 1997 was about this area called Fiorito. You see, this is the CAF system. So these faults, which are normal faults, developed along the axial zone of the Apennine chain. So you have to imagine the Apennine that was built up during the uppermost Miocene and the lower Pliocene, and then a kind of collapse that is gradually affecting all the chain. It is much more strong in the westernmost part of Italy, and it produces gradually the opening of the Tyrrhenian Sea, while these are the last normal faults at the boundary of this collapse, and they are dramatically active. So we have frequent earthquakes. You see this one down with the, I think with the 2009 L'Aquila earthquake, and these are the faults that moved in 2016. So you see extensional focal mechanism. So we were interested at that time, at the end of the last century, not very much was really known about active faults and about the behavior of these faults. So what we did at that time was to look at, this is a detail of the Cortolito basin, because we have this intramontane basin developed along these normal faults. And so we were interested in the damage zone around this fault and possibly in having some information about fluid circulation to know how deep these faults were working, if there were fluid involved into the faulting process and so on. So these are some examples of the cataclastic or photocataclastic rocks relative to the basin boundary fault and to some subsidiary faults that develop in this area. So I performed some microstructural analysis looking at the kind of deformation and sometimes the occurrence of shear extension bays related to the faults was unraveled. So you see here different openings and healing of the fractures and so on. And also into crystals, in this case calcite crystals, because the rocks I didn't mention, but we are in a sedimentary sequence, mainly composed by limestones or miry limestones in this area, and then in the outermost area we had also silicified formation. So my study were in calcite, which is a strange material because it's soft. It's not so good for fluid inclusion. It's very heavy to study fluid inclusion outside. But you see, there were nice drawing bands, very nice, but no possibility to study the inclusion because they were really tiny, not possible to study. But sometimes I got some fluid inclusion assemblages, some clusters that were useful, and some inclusions were was possible to check. In this case, you see a kind of necking down, for example, so not good to start. In this case, too much vapor. This is the meniscus here. And so probably some leakage, not good to study. So I had to figure out some inclusions to check. And at the end, I had some nice group of inclusion to measure. And both from veins coming from the basing boundary fold and from veins from the secondary folds. So what I got was an homogenization, isometric temperature. You see that gave a composition in primary inclusion around -5, -6 degrees, which is a percentage. Now I don't remember the percentage of NaCl, but not really salty, but not pure water anyway, so some percentage of NaCl. While in secondary inclusions, the melting temperature was more close to zero. So it was possible to distinguish sorry, not the secondary, these are the subsidiary folds, so secondary folds, not secondary inclusions. So it was possible to check differences in the water composition coming from the main fold and from subsidiary folds. And this allowed us to confirm the hypothesis that the main fold was going deeper and having some fluids that were circulating down to the evaporative Burano formation, which is a very important saline formation in the underground. What about the homogenization temperature? The homogenization temperature was around 120, 140 degrees. So this also confirmed that the fluids were coming from a certain depth. So we were measuring at the surface, perhaps after an uplift of the area, but the vein formation was at depth, and the fluids were circulating at least 6 kilometer depth. And in fact, then with the next studies, the epicentral position was around that depth. So this kind of study, together with the microstructural and the regional studies, allowed to say that the circulation was mainly related to shallow environment. So it was water in the bubble zone coming from meteoric water, but with some contamination from depth due to the salinity. Deeper fluid characterized by higher salinity episodically contribute to the calcite vein filling. And then the crack seal mechanism of the vein can be due to the gradual increment of the pore fluid pressure during the interseismic period. And so, thanks to the fluid inclusion, we were able to define some of these aspects, some aspects about the evolution of this fault system.
That already some are coming from the bench and the fault zone.
Yeah, all the sample comes from veins in the fault zones, extensional veins or calcite fibers along the fault plane. These were the samples. In another case, this is the place down in southern Italy between Campania and Calabria, the Monte Pulmone area. We tried to check with the help of fluid inclusion how the progressive deformation worked, if there were some change in environment during the progressive deformation of shear zones. So the question was, evolution from brittle ductile shear zone, vein array, relative that evolved from a shear zone to fold, It is due to environmental variation or strain localization. So you move from a ductile, brittle ductile environment toward a brittle environment, or it is a matter of strain localization, progressive strain that go from shear zone to brittle fault. So let's have a look. This is the area here, the Basilicata Campania area, is a quarry where there was a nice set of shear zone, conjugate shear zone, which are underlined by veins. Matteo, by the way, this is Professor Mazzoli many years ago. So we were working together in this quarry, and there were 50 of these shear zone conjugate, almost 50 of these conjugate shear zones that perhaps you can appreciate here. You see, you have vein array, another here. These are conjugate. And we are in the core of an anticline, which is at the top of a thrust. You see that the core has a sub-horizontal bedding because we are just in the core. So these are cherty limestones, Cretaceous cherty limestones, with beds between 10 and 40 centimeters deep, and they are cut by these vein arrays. Now, we were able to observe different stages of evolution of this shear zone. So, in some cases, you just have a vein array with striped vein and echelon distributed. In other cases, these veins start to be merged each other, so they get sigmoidal shape and they merge each other. The next step is fault. So fault cutting through the vein array. And of course, you have mineralization around fault, calcite fiber mainly. And at the end, these, which were normal faults, were reworked as striated faults. So what I did, I took samples from each stage of this evolution. So from the striped veins to the sigmoidal merging veins, from the fibers along the fault plates, and from the striated material, let's say fibers related to the striated material. Sorry, there were names. In fact, incipient and faulty, these are names that we gave to the several stages of deformation. And these are also the structural analysis with the main set, conjugate set of shear zones, and the movement along the plane. This is a schematic. Sorry, these are four to the values. So these are the main planes, and these are the four to the values. And this is a sketch of the shear zones, how they were organized. We made a lot of measurements in this area to get the thickness of the shear zone, the length of the veins, how they were arranged, the angle between veins and shear zone, and so on, just to calculate the amount of shear, the amount of strain. Okay, these are some sampling. These are where I took the samples. For example, one of the samples, this is another where they were merging. And these are some microstructural analysis. You see interfingered boundary of the crystal, so some ductile behavior, twinning in calcite and so on. But also here it was not easy to measure the inclusion because you have to find some crystals which are clear, not very much deformed, otherwise your inclusions do not survive. So you have to check. Okay, this is I took from the paper because I couldn't find anymore the original pictures. You have also microwaves cutting through the crystals. But anyway, you have some good place where you get a nice primary inclusion. You see here, they are all aligned along this direction. There is a tiny bubble here. They are very small, 50 microns. So they are between 5 and 10 microns dimensions. Okay. Other examples here, inclusion, nice inclusion, here, tiny inclusion, another here, and so on. These are very nice, tiny but nice. So two-phase primary inclusion, they are isolated or along growth bands or in small groups, but they are definitely primary, so they are related to the growth of the crystals. And secondary inclusion aligned along planes. You see the planes that goes through the crystal. So if on focus here and out of focus down there, it means that we have this plane of secondary inclusion going inside. And finally, the histograms relative to the inclusion, ice melting temperature, not very saline, almost pure water. So the fluids circulating were meteoric water with very low salinity. And I made also this diagram here, TH and TM, and you see they are quite well clustered. Black are primary inclusion and white are secondary ones. So not much leakage or stretching. They were quite clustered. So I was confident that this result would be good. And finally, the homogenization temperature. So the different steps, I call them V1, V2, so the single veins, the melt veins, the fourth plane, normal and stripe sleeve. And you see there are no really great differences. So trapping temperature, these are the secondary and these are the primary inclusions. Trapping temperature are almost always the same. And this is what we want to know. The environment was not changed during the evolution of the shear zones. So it's a matter of strain, localization of strain, and in fact, with all the other calculations that we got, we saw that when the strain, the amount of strain overcome 9 centimeters, you start to break and to form the fault. And so you move from the ductile to the brittle in the same environmental condition because you localize the strain. And it was a good result, nice. Okay, these are the temperature of primary and secondary inclusion. So no variation in composition and no variation in the environment. And these are the conclusion, of course. Different sets develop inclusion. They develop a constant PT condition. This condition remain essentially unchanging during normal photo development. Photo initiation is due to strain localization with a critical value of displacement, which was calculated in 9 centimeters, and shear strain gamma of 1.2. PT condition changing presumably during the exhumation. So with the secondary inclusion, presumably, of course, you start to exhumate the area and you have lower temperature for the trapping of the secondary inclusion. So at that point, you start to change the environment. Okay, so this was another question with another answer for a different problem. Now, something relative to metamorphic rocks. This is also an old paper because it's one of the first study I performed in my life of a fluid inclusionist. And it was a great experience because beside the natural sample, this work was performed in the labs of the Virginia Polytechnic in the US together with Bob Bodnar and Maxime Vitti. And so we published the result in this area. What was the question here? Can fluid inclusion texture, so not more looking to the nice shape of inclusion with the bubble and so on. We are looking to the outside shape. Can fluid inclusion texture create information on the prograde segment of the PTT part? during subduction. So you move from the surface downward with your subduction zone. You form free inclusion. What happens when you go down? Of course, you put the inclusion under a strong pressure inside your crystal. And you still get some information from these inclusions. So the area is here, is in Calabria. This is a beautiful place that also Matteo knows, because we usually perform our master course, structural geology course here for the field camp. And we go in February, January, which is winter in Italy, but that area is quite nice. It is by the seaside, and you have, let's say, always 14, 15 degrees, so it's possible to work out during the day. So in this area, what you can find by the seaside are some ophiolitic units, metabasalts and meta limestones of the oceanic cover, and they were involved in a high pressure, low temperature event, and probably they had, or at that time, these are the results from this work. Then people worked some more on this stuff, and probably this green schist patches condition was not perfectly true, but I go ahead with my work now. So probably the exhumation was faster than was expected, so there was not enough time to have a really a depletion. But anyway, we have some minerals which are typical of green schist patches. You see one of the example of the isoclinal faults in calcis. So the structures developed in these metabasalts and calcis are strong, really pervasive foliation of the first phase of the formation, with isoclinal faults inside the foliation in some kind of outcrop. They are really beautiful. And there are also post-calcite-rich veins that developed during this first stage of deformation. And then there is a second phase of deformation, which is described by crenulation, open folds that reward the first phase foliation, and so on. So we of course perform a strong structural analysis in that area, with measuring the stretching lineation and so on. So we can distinguish the D1 deformation phase, the D2 is with these open folds, and then also a third phase, which is the last one, the brittle one, with the several feature, brittle feature structures and joints relative to the last extension and the opening of the Tyrrhenian Sea. So we don't pay attention to this latter one. We were focused on, for this study, on the on some coarse calcite veins which were strongly deformed. So they were involved into the first phase deformation. So what I found inside these veins are two kinds of very different inclusions that I call type 1 and type 2. So type 1, you cannot measure here very much. They are quite dark, but they have this dendritic shape, let's say, and they are ubiquitous in the samples. Then you have type 2, which are two-phase inclusion, very nice in some cases. You see negative shape crystal inclusion with the bubble design. And I have other examples, both of the dendritic shape and the two-phase inclusion. These are in contact. Also secondary inclusion. You see these traits of secondary inclusion along field structures. Nice two-phase negative shape crystal inclusion. So from microthermometry, the type 2 inclusion, the only one I can measure with a microthermometry, they gave a trapping temperature between 140 and 160 degrees, homogeneous between quartz and calcite. So very good agreement with the result of quartz and calcite. while the fruit was really almost pure water, very solutive fluid. Now, what was interesting is at that time I was studying this sample at the Virginia Tech. Maxime was performing some experiment on the shape of this dendritic inclusion. And we found a precise correspondence between my dendritic inclusion in natural samples and this, come si chiama? Synthetic inclusion into the lab. He performed a series of experiments where you can see the trapping condition here of two different samples. So sample C300 was trapped at about 4 kilobars and 400 or 500 degrees temperature, while the other sample was trapped at 2.5 kilobars and about 600 degrees temperature. So they let the sample to equilibrate at this condition, and the inclusion to be healed inside artificial cracks in the quartz crystals. And then when everything was settled, what they did is to change the surrounding condition. So imagine that the synthetic samples goes under subduction. So first of all, they perform an isochoric exhumation, let's say artificial exhumation of the sample to go to almost room temperature. So isochoric, so nothing was changed into the inclusion. And then they perform, let's say, relatively quick barrier subduction and putting the sample at this condition 5 kilobars and for one sample and about 5.5 kilobars. And then they checked what happened to the good inclusion. And the thing was that we found almost the same kind of shape in natural samples. These are my samples, and these are the samples got from the lab experiment. So this dendritic shape is again, these are my samples, and these are, these are from the first 4 are from the lab, and these last 2 are my samples. E and F are my samples. So during subduction, the original inclusion were decrepitated because of implosion. Okay, so they went to a condition of under pressure inside the inclusion. So you got initial condition here, then you make an isothermal compression, and you get internal depression of the inclusion, so they implode, and they produce this kind of dendritic shape. They then performed also other experiments which are published by DT, going toward this other path. So isobaric cooling, isobaric heating, or decompression, isobaric decompression. Of course, isobaric decompression produce overpressure inside the inclusion, so they explode. And you get different shapes in each case. So these shapes are recognizable. And so also for destroyed inclusion, you can say something, you can get some information in order to reconstruct the PT part of your material. So my inclusion were trapped almost close to the surface, then they were subducting in somehow along this way. And at this point, they were destroyed, let's say. So they suffered the implosion and developed the dendritic shape. Then we believe that there was this Vinci spatial reactivation that perhaps was not. But anyway, during the exhumation, the two-phase inclusion were trapped. The ones at 160 degrees homogenization temperature that I showed you. So, is everything clear? I simplified very much, of course. So these were the conclusions, but I already told you, inclusion of inclusion, internal under pressure, and the secondary inclusion at 1.5 kilowatts. I want to move to the last example. I'm sorry, I can I will not be so precise because it's not a work by me, but it's very nice work by Martina Zutti. She is a former student of Camerino, and then she is, after her PhD and postdoc, she is a researcher at the University of Bari. And she had in Bari food inclusion lab, very similar to yours. So for her PhD thesis, she worked at the Elba Eye. By the way, it's a beautiful place to work. And now Elba Eye is in a position, I don't know if I have yeah. Okay, you see here. Now the purpose of this work was to compare a fossil geothermal system in Elba Eye to an active geothermal system, which is the Larderello system. Now, Larderello for Italy, as Jose has been there, we went with a trip many years ago. Larderello is really the place where the geothermal energy was born. In 1904, the first experiment to produce energy by vapor, geothermal vapor, was performed there. And the most important plants for geothermal production in Italy are there in Larderello and in Monte Annata. So there are active systems which are in production, under production. Now, the idea was to study the past to have information on the present, so transfer information, in this case, from surface, because the system is fossil now, is exhumed, to depth, to what happens in Larderello. But of course, this work stops at the fossil geothermal system in Isola. So in this area, we had exhumed rock because the geological story of this area is quite complicated. It is in a position where, at the moment, it is an eye between the Tyrrhenian Sea. So what happened there? You have, as you can see from this complex diagram, several nappes, one over the other, and the sequence of this nappe records all the stories from the opening of the ancient Tethyan Ocean in Jurassic time, and then the closure of this ocean during the building up of the Apennines, and finally, again, the opening of the Back-Arc Basin, which is the Tyrrhenian Sea. So all these nappes, all this series of nappes, which are, I think, 7 or something like that, are now dissected by low-angle normal faults, like the Giocale fault or the Monte Capanne normal fault, and high-angle normal faults that exhumed the deep rock and cut through them. So it's a complex situation, and the question. Yeah, by the way, this is this one is the study area. Now, what Martina did in this area is to see the relationship between fluid circulation into this system in an area where the cut rock were cropping out. So she wants to see what happened to the cut rock, and if fluid were circulating into the cut rock and how they were circulated, and if there were changes over time about this fluid circulation. And what she unraveled was two main fault generation. The first one here with some field pictures. No, this is not field, 2 centimeters. This is in section. These are samples or hand samples. And these are field images. You see these first generation mainly oriented northeast, southwest, and they also derive the axis, the formation of the strain axis. And then the second phase, fourth generation, which these are the attitude, and some stuff, some structure in the field relative to this second generation of things. Now, of course, she went to look at the mineralization, and in particular, she watched at the veins, so at the damage zone relative to these two generational faults. You see here, this rose diagram are relative to the vein trends relative to the faults, and the mineralization in some cases were quite complicated. So veins contain iron amphibole, chloride, and other stuff, quartz and calcite, of course, and other stuff also. And so she went to look at all these to check the chemical physical characteristics of the paleogeothermal fluids that circulate into these damage zones relative to the fault. So she performed fluid inclusion analysis and micro, mainly these two, fluid inclusion and macro Raman analysis. So let me see the other information. So what she found was two kind of different inclusions. I will show you in a minute with the images. So first one was H2O rich, but with some volatiles inside that was made mainly by CO2. And the other one was mostly aqueous inclusion without CO2. So let's have a look to the inclusions. Now, so the sample to the right are relative to the first set of inclusion of veins that were measured, where the sample were taken from the first generation faults, while these others, mainly calcite sample AC, was the second generation fault. So you see here, in some cases you have vapor liquid inclusions, so the vapor is prevalent, little liquid, but you also have liquid vapor inclusion. These are all in quartz, but there is also calcite. And again, you have liquid vapor inclusion, primary and secondary, along trades, along cracks, field cracks. Two generations, at least two. So she distinguished different fluid inclusion assemblages, and liquid vapor number one, liquid vapor number two. You see that this cracks stops against these others, so there is a relationship, a genetical, a cross-cutting relationship between the two. Now, what about the Raman? This diagram are from the Raman spectroscopy, and you see the presence of CO2. So in the vapor-rich inclusion, you have CO2. Sorry, in the vapor-rich inclusion, you have some CO2. While in the other sample of the second generation, you don't get any CO2. So this was the first distinction. You have different generation of fluids into different structures, one relative to the first set of faults and the other one relative to the second. Let's go to the microthermometry results. They are not bad, because you have from the first generation of inclusion here, these two samples, you get primary, vapor-rich inclusion and these darker ones, and liquid vapor inclusion here. These are the homogenization temperature, quite spread, so not really pretty, but not bad. Better in this case, where you have these liquids, which are in a narrower place, and vapor-rich, these are the secondary, and these liquid rule number one and liquid vapor number two. So you have two groups with different homogenization temperature. In fact, they were two different generations of cracks. Okay, And then this is the homogenization temperature versus melting temperature and the different groups. So what I can say is that it's not a perfect system. There is a little deformation, but not so bad. So you have a quite good assemblages. You see different symbols, circles, square, rounds. So they are quite distinct. Here, this latter one is about the latter stage, and you have different groups with chopping temperature that changes and go lower and lower. And this probably is due to the latter exhumation phase where all the system was cooling down. So salinity, not very much changing in all of them. Higher salinity around 5–6% for the CO2 water rich inclusion of the first generation of faults. Lower salinity for the other ones. Trapping temperature, you see the trapping temperature here for the first fault generation. They reach 300–350 degrees. Here they go around 300, let's say, as a mean value, as trapping temperature. But remember, this was a buried system, so it's zoomed down now, but it was buried. So they reconstructed in a dependent way the pressure. In this case, they reconstruct the pressure with the geology. So the thickness of the trough nap and the sedimentary sequence they could reconstruct. And in fact, what they took was this diagram thanks to the software, and they were able to reconstruct this vapor phase, two different vapor phase for the vapor rich inclusion. These are relative to the CO2, while these are the isocores for the homogenization temperature they measure into the inclusion. So the range between the measurements, you see they were quite spread, and this vapor phase, this calculation, which is made by the software for CO2 percentage, vapor phase percentage, gave this region of entrainment. And this is the maximum lithostatic pressure that was calculated, which is 0.8 kilobars. So about 0.8 kilobars. So the trapping of this inclusion was in this range, and you see that the trapping temperature is higher than what you measure as homogenization temperature in your fluid. So you measure around 350, but with the reconstruction, the trapping temperature reaches almost 500 degrees. Now, where are these up? These are the other inclusion, the liquid inclusion, or just with water, and different colors are different group of inclusions. So you see these are the liquid, the vapor-rich inclusion, this one transferred in this diagram, and these are the temperature, the homogenization temperature for the other inclusion, which are mostly lower temperature and trapping. So the interesting thing that they got from this information, because all this stuff was from the caprock of this area, is that, okay, the caprock was affected by fluid circulation, but the fluid circulation firstly was due to some fluids produced by metamorphism, high temperature metamorphism, due to the magmatic body at depth. And this metamorphism produced reaction, in particular in the argillitic rock that were belonging to the caprock, which is Argilla Parombini formation. And so the carbonization and the dehydration of these minerals during high temperature metamorphism produce fluids. And these fluids, when the first fault system developed, were channelized, went to a channel along this fault system, and they were trapped inside damage zone of the whole system. So the fluids were isolated in these narrow areas. They did not went around, they were channelized in this area. And again, when the second step of faults was formed, we had another generation of fluids, but much more meteoric. So you don't have any more any CO2 inside the inclusion, and you have mainly meteoric water and trapped in lower salinity and lower temperature, so were trapped during the exhumation. Okay. I think it is almost full. So they were able to, let's say, individually, so recognize this different step in the evolution of the fluids inside the couple. One relative to all fluids due to the metamorphism, and then trapped in the first generation of faults, and another one in the second generation of faults, much more affected by the meteoric water and trapped during the exhumation. So I think I finished. Please come to visit Maria. We are waiting for you. Any questions?
¿Alguna pregunta que les quiera lanzar al profe? Aprovechen que por ahora es gratis las preguntas y las respuestas. Sí.
Breaking from the cooling and the heating, or
Yeah. It's a good question. Because, yeah, you have to pay very much attention, even emphasize too much this aspect. But in particular, if you are working with soft minerals like calcite, for example, you are asked to perform heating first and cooling in the second time, because the freezing of the inclusion can precisely you increase the volume, so you can stretch the inclusion. So for calcite, it's better to measure the homogenization first, so you are safe and you have your measure, and then if you stretch your inclusion during cooling, that will matter. Because this does not affect the composition of the fluid, but affect the density, so the homogenization will change if you stretch the inclusion. Yeah, you can repeat many times the measurements while you are measuring, because if you pay attention to stay around the homogenization temperature and you don't go because you are chatting or you are looking at other things, and you don't go too much high with the temperature, you stay around, it doesn't matter, it works. So if you go 10, 20 degrees over the homogenization temperature, it doesn't matter. But if you go 100 degrees above, you can explode your inclusion, you can crack the sample and so on. With quartz, generally, we perform first the cooling state, the cooling part, and then the heating part, because the mineral is strong, and also if you get ice, it doesn't have to go with the kind of pressure that the ice can develop. Thanks. Other questions?
Yo tengo una pregunta, Chiara.
Sí.
A mí me queda, o sea, entiendo, no sé si es una regla, siempre es así, si la temperatura del trampamiento, es una regla, digamos, siempre es mayor a la temperatura de homogeneización. Si nosotros no podemos calcular, por cualquier motivo, la temperatura del trampamiento, ¿cómo interpretamos la temperatura de homogeneización geológicamente? ¿Sería una temperatura mínima de formación?
Minimum, it's called the minimum trapping temperature. So you get a feeling, but it's not really true. For example, in the Elba Isle, you get a feeling that was high, above 350 degrees. Now with the pressure confinement, you go 450 or 470. But anyway, you can say it's high because you record. It doesn't matter for the diagenetic environment because in fact, you are in the range, you know, you have no very high pressure in the environmental, in the diagenetic environment. So you can get an error of 20 degrees, 30 degrees maximum. But in a metamorphic environment, you can get 100 degrees difference or 150 if you cannot have any correction for pressure. So you can say it's a minimum trapping temperature.
Eh, Solamente ahí me resta, ahora queremos un segundo abrir el laboratorio ¿me pasó el celular? Por aquí. Solamente para comentarles y terminar la charla. Sí. Sí. Bueno, antes que nada, muchísimas gracias, Chiara, por la charla. Creo yo que estamos intentando que sea de alguna forma un ciclo de charlas, de etapas formativas para aprovechar el equipo que ha adquirido la escuela de Conferencia, dirigido a través a partir del doctor Marcelo Arnocio, pero hemos participado varios investigadores, contribuyendo a la decisión del equipo, para que tengan idea, la gente que está acá y los que están en YouTube. Se adquirió un equipo que posee dos turbinas Lincoln para estudio de microtermometrías, THMS G600, con rango de trabajo de menos 196 hasta 600 grados centígrados, y TC1, TC 1400 XI, con rango de temperatura ambiente hasta 1400 grados centígrados, montada en microscopio con Carl Axel Scope de 5, con un software Zen de Carl Zeiss. Y además, para no, como bien dijo Chiara, para sumarle todavía más utilidad, se pidió también una catodoluminiscencia Tex L Optical montada en el Carl Zeiss Axel 5. Esto es para que, bueno, en el marco en el que estamos atravesando nosotros y la situación que se viene viviendo últimamente en el país, es justamente para demostrar que desde acá de la universidad y con mucho esfuerzo y el apoyo de políticas públicas universitarias y de educación, garantizamos y tratamos de alguna forma, tratamos de garantizar el acceso a una educación de calidad, porque estamos convencidos que las etapas formativas de los investigadores y de los docentes rápidamente transferidas hacia ustedes, los estudiantes, y por qué no hacia los profesionales que los invitamos a que se acerquen a la universidad, se informen qué se está haciendo acá y se evite la mala información o la infodemia, como se dice, a veces malintencionada, a veces por desconocimiento, a veces por desidia también. Así que nuevamente gracias, Chiara, y espero que este sea el inicio de, como dijimos recién, el convenio que estamos tratando, y invitamos a que pasemos al laboratorio y nada. Fuerte aplauso para vos. Bueno,
Esto, ¿eh?
sí. Oh.
Vencimiento que